Okay, so now that we have learned how operators work and about commutability relations, I think it is time we formally talk about expectation values, or essentially just expected values. So, the idea behind finding an expected value with relation to some quantum operator, like the Hamiltonian operator, is that you're going to essentially find the average or the mean value of that operator, and when you do that, what you're actually finding is some measurable quantity. So we know that the Hamiltonian is actually associated with the energy of the system. So taking the average value of the operator is actually going to give us the energy eigenvalues of the system, or generally speaking, just the energy levels. So how are we going to do that? Well, first of all, we need to pose a problem. So the one I'm going to give you is what is called the infinite square well problem. So if we start off like this, we're going to have a one-dimensional problem, and it is going to be independent of time. So we're going to have the following Schrodinger equation, and don't worry too much about what this means now, because this is something that we will explore in more detail later on. But for now, let's just assume that this is basically our equation. So this is what we would call a Schrodinger equation in one dimension. And now all we're going to do is we're going to have our Hamiltonian operator acting on the wave function psi, and then this is going to give us our eigenvalues for the energy times psi. So in this case, we have the operator, or the Hamiltonian operator, equals to minus h bar squared over 2m times the second derivative operator, d squared over dx squared. Now the next thing is, we're going to be given the solution to this system, so we know that the wave function of this particular system is going to look like this, and we will derive this result later on. But now what we're going to do is we're actually going to find the energy values associated with this system. So there are two ways in which we could do that. We could pretty much just substitute these values into the Schrodinger equation we have here, and then simply solve for E. But what I want to do is I want to do it more rigorously. I am going to say we're going to take the expected value of the Hamiltonian operator, which is in essence just the inner product with the Hamiltonian acting on the wave function itself. And we're going to divide this by psi with psi. So basically the inner product of the wave function with itself. And we know that if the wave function is normalized, then we should expect the inner product with itself to be equal to 1. So in this case, I can tell you that this wave function is already normalized. And if you want to prove that, you can actually just integrate this all the way to infinity just to show that it is normalized. But that is just a step that we will not prove now. And essentially, this is just going to be equal to the integral from minus infinity to infinity of the complex conjugate of the wave function times the Hamiltonian operator acting on the wave function. And we're going to integrate over all of dx, so from minus infinity to infinity. Now, there is a trick to this, and it is that the problem is only defined within the interval. So the problem is only defined within this interval. We have 0 and L. So basically we have a box or a well, an infinite square well if you say, that goes from 0 to L, and then the wave function only exists inside those two boundaries, because if the potential is infinitely high on both these sides, then we should expect that there will be no probability amplitude of the system existing outside of this infinite square well. So this is the condition that will allow us to actually solve for this. Because remember, we're taking an integral from minus infinity to infinity. And if we want it to be a finite integral, then the function needs to vanish as it goes to infinity on both sides. Otherwise, we would just get infinity as the area under the curve. Okay, so now all we need to do to find these energy values, or the expected value of the Hamiltonian operator, is just substitute these things in here. So basically, what we're going to do is replace our limits from 0 to L, because we know the function is just going to be 0 everywhere else. So these are now our new limits. So now let's write energy equals to the integral from 0 to L. Now the wave function is going to be the complex conjugate here. This is just a real valued function, so the complex conjugate is just going to be the same thing. So we're going to have psi, And now here we're going to have the Hamiltonian operator. So we're going to have this quantity over here acting on the wave function. So d squared over dx squared acting on psi times dx. So now what I would like to do is to actually take this function and just solve for it before we integrate. So let's take this out of the equation. Let's have psi Hamiltonian on psi. So this is going to be the wave function 2 over L sine of n pi x over L. And now the next thing is going to be, we're going to multiply this by minus h squared over 2m times the second derivative of this. So we know that this is going to become cosine and then minus sine. So we're going to have a minus here. So this is going to cancel out with that to give us a plus. But now we're going to have 2 over L, and we're going to multiply the argument of this, n pi over L, twice. So we're going to have n squared pi squared over L squared. And now we're going to have sine of n pi x over L. And now that we have derived that result, all we need to do is put this together. So we're going to get, this is going to become 2L times h squared n squared pi squared over 2ml squared. And here we're going to have the following. We're going to have sine squared of n pi x over L. This is going to be what we put inside our integral. So now the energy values are going to be given by the following function. We're going to have, well, we could pretty much just try and simplify this here a little bit. So let's see what we can do. Okay, so we had the square root multiplying the square root becomes 2. This becomes L. This is probably gonna become L cubed. So, but just for the purposes of this, I'm just gonna take this whole thing out. So let's get rid of that constant by just pulling it out of the integral. So we're going to have this cancels out with that, and then we have L cubed. So this becomes h squared n squared pi squared over ml cubed. So that is what we're going to have there. And now the next thing is going to be the following, times the integral from 0 to L of sine squared n pi x over L dx. And we can use a trigonometric substitution here to find a simpler expression for this. So we're going to have h bar squared n squared pi squared over ml cubed, 0 to L of 1 over 2 1 minus cosine of 2n pi x over L, all of that times dx. And now if we go over here, we're going to have the following. So let's pull this out. Let's put this 2 here. Now we're going to have h bar squared n squared pi squared over 2ml cubed. And this is going to be x minus sine, but now we're going to multiply it by L over 2n pi, sine of 2n pi x over L. Alright, so this is going to go from 0 to L. Now all we need to do is substitute back in. So basically we notice that this is a sine function, and n in this case is just an integer, so it can be 1, 2, 3 and so on. So we know that if we put L in here, it cancels out with this, so we're left with an integer multiple of pi. So that's just going to be 0, and if we put 0 in here, that also becomes 0. So this term is going to be ignored completely. So all we're going to have is this L here. So in the end, it turns out that our energy, essentially the average value of the Hamiltonian operator of this system, is going to be 2ml squared, which is exactly the same result you would obtain if you just substitute the wave function back into the Schrodinger equation here that we started with. And this is actually something that we will derive step by step in a later video. But for now, what I want you to notice is that we pretty much just found a finite value. We have a set of values for every value of n. We're going to have a different energy level. So it makes sense just to put a subscript n here so that we know which energy we're talking about. And we actually just found this by using the concept that by taking the average value or the expected value of the Hamiltonian operator, we managed to obtain all the energy levels of this system. So I guess what I wanted to show with this video was that this is a really powerful concept, and in fact, in more general cases, this is how we would define average values and expected values and deviations and all that. This is a really, really important definition. Now, there are other things that we can do with this. Obviously, we could apply the position operator, or we could apply the momentum operator, and we could see that we would obtain values for those as well. And each quantum system that we solve is going to have a characteristic, position and momentum. And it is all tied down to this Hamiltonian operator that we talked about in the end, because the Hamiltonian operator will tell you what kind of wave function you're going to get. So this will tell you the wave function once you solve the equation. And then these two operators, all they're going to do is they're going to act on this function here, and they're going to give you a value for either the displacement or the position of a particle or the momentum it has at any point in space. So hopefully this has shown you that there is actually some really important result that comes from applying all these concepts of inner products and then just the Hamiltonian operator acting on a wave function. We actually get measurable, quantifiable results out of it. And this is probably one of the most important concepts in quantum mechanics.